My name is Vahid. I want to talk about our paper local search for Flowshop scheduling problem with setup times and blocking constraint. First of all, let's see what is the Flowshop first. Flowshop is one of the most well-known, well-known problem, famous problem in scheduling and manufacturing problems. And in the Flowshop, we have a number of jobs and a number of machines. That the layout of machines is in the series, and all job must be processed by all machines. In fact, all job must be processed by first machine 1, machine 2, and until machine M. And each job need a processing time on each machine. And our goal, our aim is to find the sequence of the problems, sequence of the jobs, actually that minimize the objective. Different objective can be defined for this problem, can be considered, but in this paper we consider one of the most famous, most used and studied objective called make span. Make span is the, when the job in the last position is finished, its processing is finished on the last machine. Know that, recall that we are to find the sequence of the jobs. So our solution representation is a permutation, a job that as none of the jobs must be repeated or missed. So our solution space or search space is too big, because in this paper, the smallest instance that we considered has 20 jobs, so it will be 20 factorial, and the largest is 500, so 500 factorial solution we will have. So it's too big. But the most of the production lines are not exactly the Flowshop. In the Flowshop, because in the Flowshop the space between each machine is unlimited. But there are inspired from real applications. We have the number of constraints are considered for Flowshop. That one of them is blocking. In the blocking, it is say that the buffer between each machine is 0 for many reasons. For example, we have considered a factory of a refrigerator, a car. The product is too big, so when one machine finishes operation of one refrigerator, and the next machine is not available, so this refrigerator can be put between two machines, because refrigerator is too big and we can we don't have a space. For example, in this example, the first one is the only Flowshop, and we have 3 machines and 3 jobs, green, red, and yellow. And in the down image is the Flowshop with the blocking. As can be seen, you can see that, for example, when machine 1 finish the operation of the red one, the red one can be operated by machine 2, because machine 2 is operating the the green job. So machine 1, that job, in fact the red job must, although its operation is finished, but must stay on that machine. So this period of time is called blocking. Various types of blocking can be found in the literature. There are all of them are explained detail in the paper, but here for the time I don't want to explain all of them in detail. But you can find it in the paper. We have 3 different blocking: RSB, RCB, and RCB star. Mostly, almost in all of the studies or papers in the literature, they consider that there is only one of these blocking between all the machines. For example, here, they consider that between machine 1 and machine 2, there is RCB, in machine 2 and machine 3, RCB, and between all of them is only one of them, for example. But here, in this paper, we consider a mix of the various of blocking, for example, between machine and machine 2, RCB, between machine 2 and machine 3, RCB, RSP, and I will explain that why we consider a mix of this. Another constraint that can be found is the setup time. Setup time is those operations that must be done, must be performed before when one job arrives to the machine. For example, actually machine should be cleaned for the next one, for the next job, or actually they need some coding, you need to enter some codes, fixing or reselling actually parts to the machines. In this paper, we consider the cider industry, that is one of the important industries in Australia, and we see that actually in this industry, and maybe there are some other industries that that we don't know yet, but in this industry, and actually there are some a new constraint for the flow shop. First of all, cider industry has a flow shop layout. And in addition, we saw that, for example, between, actually we have a mix of the blocking between different back-to-back machines, and we have setup time as well. Actually we see that not only we have blocking, but also we have setup time as well. So based on this real-world application, we propose a new model that the Flowshop with mixed blocking, not only one type of blocking, mixed blocking and setup time. Okay, here you must know that when we have blocking and setup time, again we can have two different scenarios when setup time and blocking are overlap or non-overlap. Here we consider the overlap because of the again cider industry, but I think we can find some example that actually non-overlap is used. So in this paper, we consider a model for the Flowshop that consider both mixed blocking constraint plus setup times in overlappable scenario, and we show that that is not shown here, but is shown in the paper, that this problem is NP hard when number of machine is more than 4, 5, 6. So as I mentioned, the search space in this problem is too much, it's too big. It's n factorial, that n is number of jobs, and in this paper we consider the number of jobs 100, 200, and 500. So the search space would be 100 factorial, 200 factorial. So for this reason, we propose a local search algorithm for this problem. But we propose a constraint-guided local search algorithm for this problem. I will say that what constraint-guided local, what does it mean? First of all, our local search algorithm is kind of restart algorithm. We have it's very simple structure. We have only two steps. One of them is local search, another is construct. Local search is the intensification phase, and construct is the diversification phase. In fact, in the diversification, in the construct phase, in each iteration, we create a new solution for the local search, and local search go there and actually digging down, so to find a better solution. Okay, local search, just a very quick review. Local search is algorithm. Is probably is the very simple and most used meta-heuristic algorithm in the for this, at least for this type of problems. In the local search, start from a given initial solution and try to consider whole solution around that current solution and move to the better solution if that solution actually has a better objective function. So it is clear that to move from one solution to a neighbor solution, you need some neighborhood operator. Here we use insert and swap operators because they are mostly used for this Flowshop scheduling problems. But here we said usually, but mostly jobs are selected randomly. For example, in the swap, when you have a permutation, two jobs in two different positions are selected and change and interchange their position to each other. But is it very important how to select those jobs and which jobs should be selected? That in the literature, most of them are using randomly. But here we said, no, in the literature, they select, for example, jobs randomly and then call the objective function and try to satisfy whole constraint in the objective at time of calculating the objective. But here we try to propose a specific knowledge of the problem injected to the in the search as well. And we say that we are considering and we are to try to minimize the objective of Flowshop with blocking constraint and setup time. So we must define and we must try to find those jobs that create more blocking. And they are the most problematic part of the solution. So for this reason, we propose a greedy job selection. And we say that we first of all calculate all the blocking created by each jobs, and those jobs that create more blocking should have more priorities. There are very more detail in the paper that how this greedy job selection is used in insertion, swap, and Another part of this, our solution was, our algorithm was construct phase or our diversification phase. In the diversification phase, as I mentioned before, we try to create a different solution in different area in the search space to diverse and to escape from local and a strong local optima. In this paper, we propose 3 different construct method, and considering each of them, so we will have 3 different CGLS or Constraint-Guided local search algorithm, CGLS 1, 2, 3. For the first 2, we propose 2 different dynamic heuristics based on the NEH algorithm. NEH algorithm is very famous for this problem. But NEH is a deterministic algorithm, so it will always give you a same solution. But here we need an algorithm that always, in each iteration, give you a different solution in different area in the search space to guarantee the diversity of the process. For this reason, we propose 2 different heuristic for this problem that is dynamic and create different solution that in detail explain the paper. But our main version is the CGLS 3 that we use the path relinking as the intensification, as the diversification phase. First of all, what is path relinking? Path relinking, as can be seen in the figure, suppose we have a number of different solutions in our search space, and in path relinking we have 2 solutions, initial solution and guiding solution or target solution, and we move from our initial solution to the target solution. And in this, and we create a path, and each path, in this path we have a number of intermediate solutions. And we use this one because in the literature, mainly the most of the, in the typical restart local search, typically the researchers use the generate random solution. In fact, they generate a completely new solution and go to that area after local search, generate another completely random solution. But they are not using information about the process that already used and already found by the algorithm. And it is shown that even in our paper that using completely random solution leads to generating a poor quality solutions. For this reason, in this paper, we use path relinking. Our path relinking, our guiding solution is completely random solution. And our starting solution is the best known solution so far by the algorithm. So in fact, our algorithm at each iteration moves from the best known solution to a completely new area. So, and create a number of solutions between these 2 points. And we select the best intermediate solution in terms of the objective. And this method helps our algorithm when move from best known solution to a completely random solution. And this intermediate solution actually have properties that for both area. In fact, our new solution is not completely random, is not very close to the best known or complete or to the best known solution so far, or a strong local optima. Okay. I say that first of all in this paper, because we had no time to use the real data, but in the extended version we are using the real data from the cider industry. So here we use the random instances that's very well known for this problem, but this problem is used for the first one, so we adopt those instances exactly for our problem and our model. And actually we compare our algorithm with two, again there is no algorithm or solver for this problem, so we compare our algorithm with two of the well-known algorithms in the literature that propose for related or close problems. And each of them are run 5 times on each of the 480 instances. And in addition, the error and RPD is obtained with this formula. And obviously, the smaller the RPD is better, the better the solver's performance. And in addition, we run the algorithms in 3 different timeouts to see the performance of the algorithm, actually in short and in the long timeout. And this is the main. This is the table, main tables. And to note that, and can be seen, the bold values are shown the best in each row. And note that in each of these values is average of 600 values. It's average of values, because in actually it would be very long tables. So each of these values is average of 600 values. As can be seen, CGLS perform better solution and obtain better solution compared to the other algorithms. The last row, we have a setup time CDST 125, and when we have a mix of blocking RSP and RCB. When our timeout is pi is 90, and actually for this one, just for this one, you can see actually hold the instances one by one, and the red one is our CGLS3 that can be seen obtain better solution in most of the instances. However, comparing the algorithm only based on the average of the result is a bit weak. So for this reason, a statistical test is done. We perform 99 confidence intervals, and in this statistical, when there is no overlap between 2 methods, it means that there is a statistically significant difference between those 2 methods. So you can see that our CGLS3 is statistically significantly better than all other algorithms, and even our CGLS2 still is better than 2 other algorithms. Just one point, the upper bound, I say that our search space is too much, so there is no optimal solution, not only for our problem, but also for even typical Flowshop without any constraint. So for this reason, here I'm showing the upper bounds. Upper bounds here means the best known solution in the literature by any algorithm used for these problems, actually found by any algorithm in any time. So the red one is for Flowshop without any constraint, and the blue one is a Flowshop with sequence-dependent setup time, and the purple is a CGLS3. And note that our CGLS3 is a Flowshop sequence-dependent setup time and blocking. So when you have no blocking, purple would be actually convert to the blue one. So we know that our optimal solution would be between purple and blue, so it shows that how much our algorithm is close to the best known solutions and optimal solution. Just as conclusion, a new real-life constraint for Flowshop is proposed, considering both setup time and mix blocking. A new construction method is proposed using path linking, and a constraint-guided local search is proposed that actually, unlike many of the work in the literature, inject the constraint in the search as well. In addition, there are some points that I didn't show here. For example, in the paper, you can see that we show that our constraint-guided, actually greedy job selection is better than the random one. In addition, we propose two heuristics that is better than the heuristic algorithms in the literature.